So to talk about eigenvalues, we have to talk about square matrices only. So these things only apply when A is n by n. And we say there's an eigenvalue lambda with associated eigenvector v if lambda is a scalar and v is a non-zero vector, satisfying this equation. AV is equal to lambda v. So remember, A is a matrix here and lambda is a scalar. So it's important that the vector be non-zero because, of course, if v is 0, then you just have the equation 0 equals 0, which is trivial. Another way of writing this equation, if we write lambda v as lambda times the identity matrix times v, we can then write it as the matrix A minus lambda I all times v is equal to a 0 vector. Now, it's pretty easy to show from the definition of an eigenvector and an eigenvalue that whatever v is, if v is an eigenvector that goes with lambda, then alpha v is also an eigenvector with the same lambda, where alpha is any scalar other than 0. So the reason is if you just take A times alpha v, since alpha is a scalar, you can bring it outside and change the order. And then since v is an eigenvector, we have lambda v inside, and then you regroup that into lambda times alpha v. Again, alpha being a scalar, it moves around wherever it likes. And so that shows that A times alpha v is equal to lambda times alpha v. So it's still an eigenvector. So in other words, eigenvectors aren't determined uniquely. There's an entire subspace of eigenvectors that goes along with lambda. Right? So the set of all vectors which are multiples of v is a one-dimensional subspace. The subspaces that go along with lambda can actually be higher dimensional as well if you have repeated eigenvalues. Now, usually when you start studying eigenvalues, they're computed in terms of the characteristic polynomial. So the idea is, given this equation where alpha minus lambda I times v is equal to the 0 vector, and v is a non-zero vector, that means that therefore A minus lambda I is a singular matrix. So if you have a matrix times a non-zero vector and you get 0, that must be a singular matrix. So if that's a singular matrix, then its determinant must be 0. So if you take the determinant of, here I've reversed it, A, instead of A minus Zi, I've got Zi minus A. If you take that determinant, it turns out that that's always a polynomial of degree n. And therefore, every solution of that is an eigenvalue, and so there are n eigenvalues. Eigenvalues are roots of the characteristic polynomial. So as an example, suppose we have this matrix. So we take Zi minus A, so that's Z minus 7, Z minus 8 on the diagonals, minus 2 and minus 3 on the other entries. Take the determinant, and we get quantity Z minus 7 times Z minus 8 minus negative 2 times negative 3. So this whole thing is Z squared minus 15Z plus 50. So the roots of that polynomial, it just so happens it factors easily into Z minus 10 times Z minus 5. So the eigenvalues are lambda 1 equals 10, lambda 2 equals 5. If we want to, we could then go on to find an eigenvector. So, for example, if we take lambda 1 I minus A, so we put in 10 into that matrix, we get 3, -2, -3, 2. And just by inspection, you can see that if we multiply that matrix by the vector 2, 3, then you get 6 minus 6 is 0, and in the bottom you also get 6 minus 6 is 0, and so therefore this would be the eigenvector v1, or any multiple of that would also be v1, and so on. Okay, so because the eigenvalues are roots of polynomials, they may be complex numbers. So please go ahead and check out the notes on complex numbers if you're not too comfortable with them, if you haven't seen them for a while. And of course, if A is a real matrix, then the polynomial has real coefficients, and any complex roots must come in conjugate pairs as well. So those facts are just inherited from the characteristic polynomial. Another fact that's inherited from the characteristic polynomial is that if S is any non-singular matrix, then S times A times S inverse has the same eigenvalues as A itself. And when this happens, we say the two matrices are similar. So similar does not mean something fuzzy, it means something very specific, that the two matrices have the same eigenvalues. So the idea is that if you took the determinant of this matrix, well, the identity is equal to S times I times S inverse. And then you can factor out an S on the left and an S inverse on the right. With the determinant, you can break this up into a product. And another determinant property is that the determinant of S inverse is 1 over the determinant of S, so those two cancel each other out. And we get that the two matrices have the same characteristic polynomials. So this idea of changing A to a different matrix through S like this is called a similarity transformation. Okay, so now let's suppose we have all n eigenvalues, the lambda j's, and we have n eigenvectors to go with them, the vj's. So we're just writing here the eigenvalue condition AV equals lambda v for each j. Well, if we put that together, okay, for all the different values of j, we get A times V is equal to V times D. So D is a diagonal matrix of eigenvalues, and V has the eigenvectors in its columns. Why is that? Well, remember that A times V is defined, can be done blockwise. So that's the left-hand side of that equation. V times D, on the other hand, okay, so in the first column of the answer, we get a linear combination of the columns of V using these coefficients from D, in the first column of D. So the first column, the result is just lambda 1 times V1 plus 0 times all the other columns of V. The second column is 0 times 0 times V1 plus lambda 2 times V2 plus 0 times V3 and so on. All the way out to the last column. In the last column, you take a linear combination of the columns of V, where you have 0 V1 plus 0 V2, all the way up to lambda n times Vn. And so if you just compare these two equations column by column, right, each one of those is just a statement of the eigenvector condition, the eigenvalue condition, and so that's all we're saying with this equation here. So that's true whenever we have n eigenvalues and n eigenvectors to go with them. Now, if these eigenvectors have another property, if they are linearly independent. Okay, that means there's no non-trivial combination of them, which is 0. Well, that means that since they're the columns of V, they span an n-dimensional space, that V is non-singular, and therefore we can take AV equals VD and multiply on the right by V inverse. I'm sorry, I have that wrong. No, that's right. VD, V inverse. And the V times the V inverse is just the identity. So if V is non-singular and V inverse exists, we can do this. And this is called an eigenvalue decomposition, which we'll abbreviate as EVD. Okay, now not all matrices, square matrices, have this kind of decomposition. So if a matrix has it, we call it diagonalizable. The idea is that A is similar to a diagonal matrix. Right, so V times D times V inverse is a similarity transformation. A is similar to D and D is similar to A. They have the same eigenvalues, and the eigenvalues of D are easy to read off. They're just the diagonal numbers because that's always true for a diagonal matrix. But this isn't possible for all square matrices. So the famous example would be this thing here. So it's triangular. Its eigenvalues are 1. But it has only one independent eigenvector. Or you could say its subspace of eigenvectors is dimension 1. Now, diagonalizable has nothing to do with singularity. So this matrix is non-singular and non-diagonalizable. But here's a matrix which is non-singular and non-diagonalizable. And here's a matrix which is singular and diagonalizable, and so on. So the two properties really have nothing to do with each other. Okay, in MATLAB you can find eigenvalues just by typing eig of A. That gives a vector of the eigenvalues of A. If you ask for two outputs, then it gives you the two matrices V and D. So, as with many commands in MATLAB, it behaves differently depending on whether you call it with one output argument or two.